So let's try to solve this one. Till now we were dealing with problems involving a single object or a single body. Now this is a case where we are having a system of connected bodies. So now let's see how to handle a system that is a combination of connected bodies. So what is given in the problem is that we are having a pulley and there are two blocks connected to it. Okay, I'm calling this as block 1 and this as block 2. So one block is having a weight of 300 Newton, other one is having a weight of 450 Newton. And we know that as these blocks are connected using a frictionless pulley, the tension in the cable will be same in both sides, and I am calling it as T. And we know that as the right hand side block is having larger magnitude of weight, the system will be moving like this. This 300 Newton will tend to move upward and 450 Newton will be moving downward. And we know that the acceleration for both these blocks will be same, that we have already discussed while we discussing the previous topic. Because the distance moved by this cable and distance moved by this cable will be same within the given time. So acceleration will be same, displacement will be same, and velocity will be same. Okay, and these are only in terms of magnitude, but when we consider the direction, these are having opposite directions. Okay, magnitude wise both the objects will be having equal displacement, equal velocity and equal acceleration. Okay, so now we are going to find this. So for the first object I am calling it as D1, V1 and A1, A2, V2 and D2. Now we are going to apply our work energy principle. So work energy principle says that force times distance or displacement, not distance, displacement, is equal to half times mass into V square minus U square. So this was pretty easy when it was a single object. When there are connected bodies, this is a system. So this whole equation can be rewritten in terms of the system. Okay, so total work done equal to total change in kinetic energy. Okay, so that is total work done equal to change in kinetic energy for the total system. Okay, so we are going to calculate this. So first I am going to work on the work done part. Okay, work done total will be equal to work done by body 1 plus work done by body 2. Okay, the sum will give me the total work done. Now I need to calculate so I'm calling this part as say WDT. Now what is the work done by the object 1? So we need to define the direction before we are substituting the values. So I am considering this as my positive direction. So D1, V1 and A1 are positive, D2, V2 and A2 are negative. So we know that work done is equal to net force in that direction multiplied by the distance. So for block 1 or object 1, the net force is T minus 300, right? T is acting upward in the positive direction, 300 downward. So T minus 300. Okay, that is the net force for object 1 and it is having a displacement D1 in the positive direction. Plus, I'm considering block 2. So T minus 450. T is upward, 450 is downward. So T minus 450 and the displacement is in the opposite direction, which means minus D2. And we know that D1 is equal to D2 and I'm calling it as D. So total work done total is equal to D into T minus 300. Then there is a minus here. So minus T minus 450. as d1 equal to d2 equal to d. I'm taking it outside. So I'm going to get the value as, here there is plus t, here there is minus t, they cancels out. Minus 300 minus of minus 450. So what I'm going to get is 450 minus 300 d, which is equal to 150 d. So that is the total work done. So that is the left hand side of my equation. So I have my LHS. Now I'm going to work with the right hand side of the same equation. So what is the right hand side? So it talks about total change in kinetic energy. So just like what we did here, we are going to do here also. So delta KE total is equal to delta KE, that is K is kinetic energy, plus delta KE of 2. Now I'm going to try that. So what is delta KE1? Okay, what is delta KE1? Let's see that. So delta KE1 is half into M1 into V1 square minus U1 square plus half into M2 into V2 square minus U2 square. And we know that the initial condition said that the block is at rest. So both U1 and V1, okay, both U1 and U2 are 0 meter per second because the block was in rest. And now it have attained some velocity. Oh, I'm sorry, it is said that the values are 2. They are not in rest. Okay. The velocity changes from 2 meter per second to 4 meter per second. That's what is said in the problem, not rest. It was 2. Okay. So I'm going to substitute those different values here. So how will this equation becomes? So half into M1 is 300 by G into V1. Okay. V1 is in the positive direction. I'm squaring it. Okay. Minus U1 is also in the positive direction and it is given as 2 square plus half into 450 by G into minus V1 square minus 2 whole square. Okay, are you able to appreciate that? It's because the V2 and U2 are in the negative direction. So both these values should be negative. So, and we know that when we square a term which is negative, it becomes positive. So V1 and V2, in the problem it is given that the value of V1 is 4 meter per second. V2 is also 4 meter per second. Hence, this whole equation, that is the right hand side, delta KE total is equal to, I am taking out the common terms, that is half into 1 by G, okay, that is a common factor, 300 into 4 square minus 2 square plus 450 into 4 square minus 2 square. Okay, that is my right hand side of the equation. So I have both the LHS and RHS. Now what I can do is I can just equate the LHS and RHS. So LHS says that 150D is equal to the right hand side, which is half into 1 by G into 4 square minus 2 square, that is 16 minus 4, 12 into 300 plus 450. Okay, so what will I get? I will get the value of D on solving this equation as 3.06 meter. Okay, the distance traveled, or the displacement of both the blocks, and the distance traveled is 3.06, displacement for block 3000 Newton, 300 Newton will be plus 3.06 as per the sign convention, and for block 2 it will be minus 3.06 according to the sign convention we chose. And the other part of this question is to calculate the tension. And how to get the tension? So we are trying to calculate the value of T. This is what we have already got till now. So it has been redrawn. So we got the displacement, initial velocity and final velocity is given in the problem. So for block 1, these values are positive according to the sign convention we chose, and for this block these values are negative. So now we are going to calculate the value of T. The value of T can be calculated in many ways, and I am going to discuss two ways. Okay, one, we can directly apply the work energy principle, or we can use the basic equations of motion or laws of motion. Okay, so what I'm going to do is I'm going to consider one block, say block 1. So if I consider block 1, okay, it is having 300 Newton acting downward, T acting upward, and it is having an acceleration in this direction. Fine. So what will be this A? What will be the value of A? If we are seeing this problem now looks familiar to that of our D'Alembert's principle, right? If I'm trying to write the D'Alembert's principle for this condition, what I will be getting is that I need to have this positive direction. I am using this as the positive direction. So I'll be getting T minus 300 is equal to 300 by G into A, right? So if I have the value of A, I can get the value of T. Now how to find A? We have the basic equations of motion. What are the parameters that are known to us? We have D, we have U, we have V. So it rings a familiar equation, V square equal to U square plus 2AS. The value of S is available, 3.06. U is available, V is available. I can calculate the value of A. So I can write 4 square is equal to 2 square plus 2 into A into 3.06. From this I will get A equal to 4 square minus 2 square divided by 2 into 3.06, which will give the value 4 square minus 2 square divided by 2 into 3.06. I am going to get a value as 1.96 meter per second square. Once we have this value, we can back substitute in here. So this equation, say this be equation 1. So equation 1 becomes T minus 300 is equal to 300 by 9.81 into 1.96, which implies T is equal to, let's calculate that. So 300 divided by 9.81 into 1.96 plus 300. I'm going to get the value as 359.94 Newton. Okay, that's one way of solving for the value T. That was using the basic equations of motion and D'Alembert's principle. If you don't want to use this thing, we can directly apply our work energy principle. Okay, so for work energy principle, I'm considering this same block. Okay, and now what are the parameters we have? We don't have the value of A, but we have the value of V as 4 meter per second, U as 2 meter per second, right? And the value of D is known, which is 3.06 meter. So if you have these many parameters, you can directly apply your work energy principle. I am applying the work energy principle. So net force in the direction of displacement is T minus 300, that is F into D is equal to half m V square minus U square, our work energy principle. net force T minus 300, T is positive, 300 is opposite, so minus 300, so equal to half into 300 divided by G into V square minus U square, that is 4 square minus 2 square. Directly from this you can get the value of T, and on solving this also you are going to get the value as 359.94 Newton. Okay, so these are parallel approaches of solving for T. So you need to think about which is the best way of solving. Okay, all the ways are going to give you the right solution, but the best way, you need to depend upon the parameters what you are having. If you are having acceleration in hand, you can think about D'Alembert's principle to solve for a force. If what you have is the initial and final velocity along with displacement, the easier option is to go for our work energy principle. So this is basically the case when we are dealing with connected bodies. So when we are having connected bodies, total work done is equal to change in total kinetic energy. Okay, when it's a single body, it will be work done is equal to change in kinetic energy. When it's a system, is going to be total work done is equal to total change in kinetic energy.